Okay, let's think back to your study of systems of equations, which hopefully you did last year. If I have a linear equation like y equals 3x plus 4, I can represent that as a graph. It looks like this. So every point on this line is a solution to this equation. For example, if I plug in the point 0, comma 4, 0, comma 4, and I stick it in, I get 4 equals 3 times 0 plus 4. Is that a true statement? Yes. And every other point that lies on the line will be a solution to that equation. So there are an infinite number of solutions. Okay? Well, if I introduce a second line, um, let's do, so if I did something like y equals x plus 2, that would look something like this. And that line also has an infinite number of solutions. Are there any solutions that satisfy both equations where they cross? So I don't know if I drew that very well, but that single point is the only point that satisfies both equations. And you can graph them and figure out what that is, but there are also other methods. One of them is called substitution. So this first equation is saying for every y value, there are x values that satisfy this equation. And then down here, we have the same thing. For every y values, there's a second set of x values that satisfy this equation. What we want to know is, are there x and y values that satisfy both? And one way to figure that out is replace this y with this y. But that y is also known as x plus 2. So we're going to substitute x plus 2 in here, and I get x plus 2 equals 3x plus 4. Subtract x minus 4. So I get negative 2 equals 2x. So x equals negative 1. What does that tell me? Negative 1 is the x coordinate to the intersection. So if I go back to the graph, right here at negative 1, this point is negative 1 comma something. So to find the second half of the answer, I need to plug negative 1 back in. And because I have an x and I'm looking for a y, I want to use an equation that says y equals. And in this case, they both do, but in the future, that's not going to be the case. So I stick that in here. Negative 1 plus 2 is 1. So this point is negative 1 comma 1, and that is the only solution to this system. So systems find the intersections of sets of equations. And in the future, we're going to look at systems that are not necessarily linear. This system actually has two solutions. So if I go back to the original, if I plug in negative 1, 1, it's going to work in both equations. So 1 equals 3 times negative 1 plus 4. Is that true? Yes. And over here, 1 equals negative 1 plus 2. Is that true? Yes. And that is the only point that will satisfy both. Each line has an infinite number of solutions, but those solutions only intersect once. Well, is it possible to have something other than one solution? If they're linear, if you have two lines, is it possible to have something other than one solution? You could have, if they're both linear, they either touch once, or they never touch, or they always touch. So, So I could move this line. I mean, that's no solutions. But if I actually graph the same line twice, then careful, it's an infinite number of solutions. Does it mean every point works? No. Every point on the line works. So the answer to this would be infinite solutions. It doesn't mean every solution. It means every point on the line is a solution. Okay? So if we look at your worksheet, we look at number 1. This is already set up for substitution. You can see one of the equations is written in y equals form, which is nice. So I'm going to take this information and I'm going to plug it in here. And that turns a 2-variable equation into a 1-variable equation. Essentially, we got rid of one of the variables. So negative 2x minus 3 times 6x minus 11 equals negative 7. Now that I have a single variable, I just simplify. Negative 2x, this is going to give me minus 18x, and that's going to give me plus 33 equals negative 7. So that would be negative 20x. I'm going to subtract 33, and I get negative 40. So x equals 2. That's half of my answer. If I look back at the original equations, which one is easier to plug the 2 into? The top one, because it's already solved for y. So I plug 2 in here, and I get 12 minus 11, which is 1. That's my solution. That make sense? Okay. Look at number 7. We have a little bit of a problem on number 7. In order to substitute, we either need an x equals or we need a y equals. We don't have either. So I need to create an x equals or a y equals. Which one would be easier to solve for? The top one, and we would solve for y. So I'm going to add this over. So this would be negative 5x, and this is a little bit tricky. It says take the opposite of whatever y is. Well, y is 6 plus 4x, so negative y would be negative 6 minus 4x equals 21. And then you can solve that. But this says take the opposite of y. And y is 6 plus 4x, so the opposite of y is negative 6 minus 4x. Okay? Then you could continue to solve that. Turn to the back side. Look at 17. 17's a little bit harder. I don't have any easy variable to solve for. So what should I do? Okay, can I simplify one of the equations before I get started? I can divide the bottom one by 3. Is that going to change the graph? When we did quadratics and we factored out numbers and dropped them, it changed the shape of the graph, but it didn't change the roots. But that's because we were only dividing one side of the equation. In this case, if we divide both sides by 3, it has no effect on the graph. So that would be x plus y equals negative 1. And now I could solve for either x or y. Does that make sense? Okay, look at 19. Can I simplify one of the equations? No. So what do I need to do? I need to either pick an x or y and solve for it. Which one would be the best option here? Probably the bottom x, because it's positive. So I'm going to add 7y. And I get 2x equals 7y minus 17. Now what? Divide by 2. So x equals 7y over 2 minus 17 over 2. Let's actually work this one out. What's my next step? I need to plug this in for x here. So negative 5 times 7 is negative 35y over 2. And then negative 17 times 5, that's going to be 85. Do we want to do that? So plus 85 over 2 minus 8y equals 17. Now what? Okay, how would I simplify? I could, that's a really good idea. I could just times everything by 2. What would that do? That would eliminate the denominators, and as long as I do it to both sides, I haven't changed anything. So if I times the whole thing by 2, I get negative 35y plus 85 minus 16y equals 34. And now that's a lot easier to deal with. When I solve this, which equation do I want to plug? So when I get my y equals, which equation do I want to plug it into? This one. Why this one? When I get my y equals, if I'm looking for x, it's always easier to plug it into the equation that says x equals. And every time you use substitution, one of them will either say y equals or x equals. And that's the one you want to plug it into, because then you just do 7 times y divided by 2 and subtract this and you're done. Okay? Well, what if I had one that looked like this? And so let's plug this in here. Negative 2x plus 2x minus 4 equals negative 4. What do you notice? The x's cancel, and I'm left with negative 4 equals 4. Right, so what this is saying is x has no bearing on the answer. So if you end up with 0 equals 0 or 6 equals 6 or 5 equals 5, that means that your graph is actually 2 lines right on top of each other. How do I tell if they're parallel? So what I would do is take one of these lines and move it up or down. So if I change this, say, to a negative 3, I would change this to a negative 3, and the x's still cancel, and I end up with negative 3 equals negative 4. When is that true? Never. So this has no solution. So 2 equals 2 means you have an infinite number of solutions. And if you have something like 4 equals 6, that means you have no solutions. There are no intersection points. All right. Get to work. Good luck.